The second topic I want to discuss is I want to talk about robustness of graph neural networks. So the question is, how robust are these models against, let's say, adversarial or any other type of attack? So this is motivated by kind of more broader field of deep learning, where in recent years we have seen impressive performance of deep learning models in a variety of applications, especially, let's say, in computer vision, natural language, and so on. But what has been shown is that if these models are applied to the real world, and we have different types of actors in the real world, then the question becomes, how robust are these models to various kinds of attacks? And one example is a notion of an adversarial attack, where, for example, you can take the original input image and ask the neural network, what do you think this is? And the neural network is going to say, oh, it's a panda. But what you can do then is very slightly perturb values of the pixels, you add a bit of noise, and now the neural network will get totally confused, and it will say, oh, it's a gibbon, right? It's a monkey. So the point being is that to a human, when we look at this, they both look like images of a panda to us, but by being very careful and systematic, very adversarial, you can change the prediction of the neural network. And these types of adversarial examples are also reported for natural language processing model, audio processing, and the point is that the adversary can very quickly change the prediction of our model by only slightly manipulating the input. So the existence of adversarial examples prevents reliable deployment of deep learning models in the real world, because adversaries may try to actively hack the deep learning model and kind of sidestep it. And the model performance this way may be much worse than what we'd expect, right? And what has been found is that deep learning models are often not robust. This is a very active area of research to make these models robust against adversarial attacks or adversarial examples. So let's look in this part of the lecture about how would you formalize the notion of adversarial example to graph neural networks, and are graph neural networks robust to adversarial examples? And the premise is that if common applications of graph neural networks involve, let's say, platforms that are accessible to the public, or that there is some financial monetary interest behind them, then these types of attacks may happen. So, for example, in recommender systems, social networks, and search engines, there's always some types of attackers who may want to manipulate the system. So the adversaries have incentive to manipulate the input graphs and basically try to change or flip or hack the predictions of the graph neural network. So how are we going to set up the framework to study robustness of graph neural networks? To study robustness of graph neural networks, we are going to specifically consider the following setting. We are going to look at semi-supervised node classification, and we are going to use the graph convolutional neural network model just as an example. And the idea is, right, we have a partially labeled graph. So here's the example. We have a graph. We are thinking about node classification. Nodes have features. Some nodes already have labels, and we would like to predict labels for the other nodes, as I show here. So then the question is the following, right? What we are going to do is we are going to first describe several types of attacks that the adversary may do. Then we are going to talk about how a graph neural network or a GCN how we could try to hack it. And this means that adversary needs to know what underlying model we are using. And then we are going to mathematically formalize the attack problem as an optimization problem. And then I'll show some empirical results to show how vulnerable GCNs are to adversarial attacks. So let's first talk about what would an attack to a graph look like. And we are going to talk about direct and indirect attacks. And in particular, the way we are going to think about this is the following. Let's say there is a target node T whose label prediction we want to change. And let's say that there are some other nodes in the network, let's call them S, that the attacker can modify. So these are the nodes that the attacker controls. And now what can the attacker do? So let's say that there is a direct attack, and a direct attack means that the attacker is the target node, right? So the attacker owns the target node. So what the attacker can then do, the attacker can modify the target node features. For example, they can change their social network profile, they can change the website content. They can also add connections from the target to other nodes in the network. Like, they can buy likes, they can buy followers, they can make friendships, things like that. And they can also, of course, decide to remove some connections. They can unfollow users, they can drop friendships if that would allow them to flip the classification label for that target node that they own. So this is what we call a direct attack, because the attacker owns the node. The node that the attacker wants to flip is the attacker. So for example, if you think about some kind of spam detection, the attacker may want to say, the social network is classifying me as a spammer. What do I need to change so that the social network won't classify me as a spammer anymore? And they may change their attributes, they may change who they follow, or they may drop some of the links in the network. There is also a second type of attack which we call an indirect attack. And in an indirect attack, a target node is not the attacker node. So it means that the attacker does not control the target, but the attacker can control some other nodes in the network, and the attacker can change, let's say, the features of those nodes. So the attacker can change the connections of those nodes, and attacker can also basically add them, or they can remove those connections. And what is a realistic example for this case? It is that, for example, the attacker wants to harm some other, let's say, innocent node in the network. So the attacker is going to change the properties of the nodes it controls to perhaps change the label of the target node they don't control. So perhaps the target node is not a spammer, but the attacker wants somebody to be excluded from the network, so they want them to be labeled as a spammer. So they are going to now change the network structure, the connections to the target node, so that the neural network is going to classify the target node differently, even though the target node has no clue that they are being under attack. So how are we formalizing the adversarial attack? The goal is that we want to maximize something subject to some constraints. And the idea will be that we want to maximize the change of the target node label. So we want to change the target node label subject to very small graph manipulation, right? We want to manipulate the underlying graph as little as possible, such that the class probabilities of the target node are going to change, right? Basically, the idea is that if the graph manipulation is too large, it will be easily detected by the agent, by the social network, and it will say, hey, there is an attack going on. But if an attack is successful, then we should be able to change just a small number of edges, maybe a few features here and there, and this will be kind of unnoticeably small manipulation that is going to flip the prediction, let's say the class label for the target node significantly. So the way we want to think of this is we'll say perhaps there is a class or a label to which the target node gets classified right now. So what we want to do is we want to decrease the probability of the correct class, and we want to increase the probability of some other chosen class, let's say class 3 in our case. So how are we going to formalize this mathematically? We are going to say that we have the adjacency matrix of the original graph, and we have the feature information of nodes of the original graph. And then we'll also have A prime and X prime to be manipulated graphs. So these are the graphs after the attack, after we have manipulated them. And we'll have the adjacency matrix and we'll have the feature matrix. And our goal or assumption is that the manipulation is small. right? Our goal is that this manipulation, the change in the adjacency matrix, the change in the node features is unnoticeably small. So basically we want to preserve basic graph statistics like degree distribution, node feature statistics, and so on. And as I mentioned, the graph manipulation can either be direct, changing the node and features and connections of the target node, or it can be indirect, which means we may want to change the connections and features of some other nodes in the network with the hope to change the label of the target node. So now that we said what we want to do, let's formalize it. So we will be given a target node V, and what the system is going to do, let's say the social network is going to learn the original, the classifier over the original graph, right? So it's going to say, oh, let's, define this likelihood over the training data, and let's optimize our neural network model parameters over the training data. And then, now that the model has been trained, how is the prediction going to look like? We'll say, for this target node of interest V, let's classify it into the class that our predictor F, our neural network with parameters theta star that we have trained, applied to this graph. This is our prediction, right? We are going to predict the class for this node V that has the highest predicted probability, just kind of standard stuff. Now, the attacker comes into play. So what the attacker is going to do, the attacker what they can do is they cannot change the parameters of the model, right? The model parameters cannot be changed because, the social network, whoever the operator, has already trained the model and has deployed it. So the model parameters won't necessarily be able to be changed. So what we can do in this case is that the GCN, the way we will think about it is that we are going to think about it that the GCN will now be learned over the manipulated graph, right? So basically we are going to change A to be A prime, and we are going to change X to be X prime. And now we are going to train over this manipulated graph, and we are going to get a different set of parameters. And then the GCN's prediction of the target node may change, both because the input is different as well as because the parameters we learned will be different because we learned them on a different graph and with different node features. And we want the prediction to change after the graph is manipulated, right? So we want the class for node V after manipulation to be different than what the class was before the manipulation. So we want to flip the class. So the way we are going to do this is the following, right? The way we are going to do this is to say we want to change the predicted probability of a class of a given node between the true class and the manipulated class, right? So here I'm saying F is outputting the probability for a given node to be of a given class. So here I want the predicted log probability of a newly predicted class C star prime to increase, while I want to decrease the predicted log probability of the originally predicted class. We want this term to decrease and we want that term to increase. So we are going to formulate this into this delta function delta that is basically changing the prediction on the target node V. It is a change in likelihood of the correct class versus likelihood of the manipulated class. And the way we make this term, this delta high, is to make this probability here as small as possible, and we make this probability here as large as possible, right? We want this to be close to 0 and we want this to be close to 1. So we want to increase the first term, the left term, and we want to decrease the second term. So the way we can write this out as an optimization problem, we want to say we want to do the argmax over the underlying graph structure and the feature vector, where we want to maximize this delta, right? This delta function of the change in the prediction on the target. Subject to the constraint that the manipulation of the graph structure and the feature vector is as small as possible. And ideally what we'd like to do is solve this optimization problem. The challenge in optimizing this objective if we are an adversary is that the adjacency matrix A is a discrete object, so you cannot take gradients against A to decide what edges to manipulate. And that's the first challenge. And then the second challenge is that for every modification to the adjacency matrix and the feature vector, we need to retrain the underlying graph neural network to see whether the prediction will flip or not. And I won't go into more details here. And here's a paper you can read to learn more about this. But essentially, the idea here is that we want to manipulate the graph structure and the feature vector as little as possible, so that the predicted label of target node V is going to change as much as possible. So imagine we are now able to solve this optimization problem, and we can ask ourselves how easy it is to find these strategically placed edges and changes in the feature vector that would let the model to completely wrongly make predictions on a given node. So here we are working on a semi-supervised node classification task with graph convolutional neural network model on a paper citation network with 2,800 nodes and about 8,000 edges. And this is a 6-way classification task. And what we are doing here is we are looking at a set of nodes that belongs to the class 6. And we ran the graph neural network, we trained it 5 times from random starting points. And here we are saying, what is the predicted probability of these nodes that belong to class 6? And you can see that they have high probability. So our graph neural network is learning well. Now imagine we are an attacker and we say, we want this class 6. So basically research papers that belong to topic 6. We want to manipulate the underlying graph structure to make them belong to class 7. Right? So this means we are going to change the adjacency matrix and see if we can flip their labels. And what is interesting is if we use this framework and ask how many edges do we need to manipulate in a direct adversarial attack, it turns out that GCN's prediction will flip after modifying just 5 edges attached to the target node. So here I show you for a given target node in 5 different retrainings, just kind of 5 different instances. We see that every single time we were able to flip the label of this target node who was of class 6 to be now of class 7, and the model is super confident that this node belongs to class 7. Even in reality, it is in class 6. And to summarize this robustness of graph neural networks against attacks, this is summarized here, where 0 would mean is classification margin. Intuitively, you can think a bit about how confident is or how correct is the classification. So if it's positive, it means the classification is correct with a big gap. So we are very confident in correct classifications. And if the classification margin is negative, it would mean we are wrong, and we are wrong by a lot, right? We assign a high confidence to the wrong prediction. And we see that with no attacks, the graph neural this is individual nodes here. We see that for majority of the nodes, the graph neural network is able to make correct prediction, and it is very certain about its prediction. And the prediction performance is not perfect, so there are a few mistakes, but those mistakes are also kind of borderline. The network is unsure about the classes of these nodes. Now, if we apply a direct adversarial attack, then you can see how we can very easily change the neural network to basically always predict, to always make a mistake and be super confident that it in the wrong class. So assign high confidence in the wrong class. So this is a direct attack, direct adversarial attack. Here is what would happen if it's still a direct attack, but it's a random attack, meaning we don't adversarially, strategically change the edges, but we add edges at random. And you see that basically the neural network will get confused, but not so badly, right? It still majority, it is making correct predictions. So definitely decreases performance, but not so drastically. If you look at indirect attacks, where we basically now manipulate other nodes in the network and see if we can change the label of the target node, here you see again we are able to do this quite well, meaning for quite a few of the nodes we are able to flip their label. So what this means is adversarial direct attacks are very strong and they significantly worsen GNN performance. Random attack is much weaker than adversarial attack and somewhat decreases the performance, while indirect attack is less effective than direct, but more effective than direct random attack. So what do we conclude from this is that if the adversary has access to the full network, has access to the data and can manipulate it, then it is very easy to change the predictions of these deep learning graph neural network models. So to summarize, we studied the adversarial robustness of graph convolutional neural networks applied to semi-supervised node classification. We consider different attack strategies, different attack possibilities in graphs. We talked about direct attacks as well as indirect attacks. We then mathematically formulated the adversarial attack as an optimization problem. So this is the optimization problem that the adversary has to solve. And we looked at some examples to empirically demonstrate that GCN's prediction performance can be significantly harmed by adversarial attacks. So what we conclude is that GCN is not robust against adversarial attack, but it is somewhat robust to indirect attacks as well as to random noise. And this topic of robustness of these types of methods is a topic of active research and a very fruitful research area.